The foundational paradigm of deep learning is the optimization of a static, high-dimensional weight matrix. While this has proven remarkably effective, it models learned knowledge as a single, deterministic point estimate for each connection. Today, we will explore and demonstrate a significant departure from this paradigm, the Syntron architecture. The Syntron architecture represents a fundamental paradigm shift in the formulation of a neural network layer. It moves away from the concept of a static, learned weight matrix and toward a dynamic, probabilistic model of computation. The core substitution that defines a syntron is a generative process. The first one is the primitive basis. The network learns a shared, globally optimized library of fundamental computational operators. These are the primitives. These operators are abstract and domain agnostic. In a fully connected layer, a primitive might be a simple scalar multiplier. In a convolutional network, as we'll see later, it could be an entire 3x3 kernel. This set of functions forms the universal computational vocabulary available to the entire network. Second, the mixture distribution. Instead of a single weight, each connection's mechanism maintains a vector of logits. These logits parameterize a categorical probability distribution over the set of primitives. This distribution represents the network's posterior belief in the utility of applying each primitive for a given input. It is the network's learned local policy for selecting an operation from its shared vocabulary. So the effective operator for a connection is no longer a stored parameter. It is an emergent expectation, computed on the fly as the weighted sum of all primitive functions, where the weights are their selection probabilities. The connection has been transformed from a passive wire into a dynamic computational unit that formulates a new operational plan for every forward pass. This probabilistic foundation enables a suite of advanced features that are intractable in traditional static networks. One such feature is an explicit working memory. Each syntron connection maintains a buffer of its recent activity, storing a trace of the most recently used mixture weights. This provides the network with a short-term memory of its own internal decisions, forming a basis for higher-order adaptation. Perhaps the most powerful feature is dynamic structural plasticity. The network can modify its own architecture during training. It does this by monitoring its own computational state via a metric called tail interest, which quantifies a state of productive confusion by combining the entropy of its mixture distributions with the variance of its activations. When this metric exceeds a threshold, the network's control mechanism determines its current vocabulary is insufficient and triggers a birth event, adding a new primitive to its shared basis. This new primitive is warm-started, based on the statistics of existing primitives, and the optimizer's state is carefully reset to ensure a stable transition. This represents a shift from designing a static architecture to designing a system with the meta-ability to design itself, growing in complexity only when its own state indicates a need for greater representational power.